VTEC is a system developed by Honda to improve the volumetric efficiency of a four-stroke internal combustion engine. The VTEC system uses two camshaft profiles and hydraulically selects between profiles. It was invented by Honda engineer Ikuo Kajitani, and was the first system of its kind. It is distinctly different from standard VVT, which advances the valve timing only and does not change the camshaft profile or valve lift in any way. Context and description: Japan levies a tax based on engine displacement, and Japanese auto manufacturers have correspondingly focused their research and development efforts toward improving the performance of smaller engine designs through means other than displacement increases. One method for increasing performance into a static displacement includes forced induction, as with models such as the Toyota Supra and Nissan 300ZX, which used turbocharger applications, and the Toyota MR2, which used a supercharger for some model years. Another approach is the rotary engine used in the Mazda RX-7 and RX-8. A third option is to change the cam timing profile, of which Honda VTEC was the first successful commercial design for altering the profile in real time. The VTEC system provides the engine with multiple cam lobe profiles optimized for both low and high RPM operations. In basic form, the single bearing shaft lock of a conventional engine is replaced with two profiles, one optimized for low RPM stability and fuel efficiency, and the other designed to maximize high RPM power output. The switching operation between the two cam lobes is controlled by the ECU, which takes account of engine oil pressure, engine temperature, vehicle speed, engine speed and throttle position. Using these inputs, the ECU is programmed to switch from the low lift to the high lift cam lobes when the conditions mean that engine output will be improved. At the switch point, a solenoid is actuated which allows oil pressure from a spool valve to operate a locking pin which binds the high RPM cam follower to the low RPM ones. From this point on, the valves open and close according to the high lift profile, which opens the valve further and for a longer time. The switchover point is variable, between a minimum and maximum point, and is determined by engine load. The switch down back from high to low RPM cams is set to occur at a lower engine speed than the switch up to avoid a situation in which the engine is asked to operate continuously at or around the switchover point. The older approach to timing adjustments is to produce a camshaft with a valve timing profile that is better suited to high RPM operation. The improvements in high RPM performance occur in trade for a power and efficiency loss at lower RPM ranges, which is where most street-driven automobiles operate a majority of the time. Correspondingly, VTEC attempts to combine high RPM performance with low RPM stability. History: VTEC, the original Honda variable valve control system, originated from REV introduced on the CBR 400 in 1983, known as Hyper VTEC. In the regular four-stroke automobile engine, the intake and exhaust valves are actuated by lobes on a camshaft. The shape of the lobes determines the timing, lift and duration of each valve. Timing refers to an angle measurement of when a valve is opened or closed with respect to the piston position. Lift refers to how much the valve is opened. Duration refers to how long the valve is kept open. Due to the behavior of the working fluid before and after combustion, which have physical limitations on their flow, as well as their interaction with the ignition spark, the optimal valve timing, lift and duration settings under low RPM engine operations are very different from those under high RPM. Optimal low RPM valve timing, lift and duration settings would result in insufficient filling of the cylinder with fuel and air at high RPM, thus greatly limiting engine power output. Conversely, optimal high RPM valve timing, lift and duration settings would result in very rough low RPM operation and difficult idling. The ideal engine would have fully variable valve timing, lift and duration, in which the valves would always open at exactly the right point, lift high enough and stay open just the right amount of time for the engine speed in use. Dohc VTEC, introduced as a Dohc system in Japan in the 1989 Honda Integra Xi, which used the 160 bhp B16A engine. The same year, Europe saw the arrival of VTEC in the Honda CRX 1.6i VT. using a 150 bhp variant. The United States market saw the first VTEC system with the introduction of the 1991 Acura NSX, which used a 3-liter Dohc VTEC 5.6 with 270 bhp. Dohc VTEC engines soon appeared in other vehicles, such as the 1992 Acura Integra GSR, and later in the 1993 Honda Prelude VTEC and Honda Del Sol VTEC. The Integra Type R available in the Japanese market produces 197 bhp using a B18C5 1.8-liter engine, producing more horsepower per liter than most supercars at the time. Honda has also continued to develop other varieties and today offers several varieties of VTEC, such as iVTEC and iVTEC Hybrid. SOHC VTEC, as popularity and marketing value of the VTEC system grew, Honda applied the system to SOHC engines, which share a common camshaft for both intake and exhaust valves. The trade-off was that Honda's SOHC engines benefited from the VTEC mechanism only on the intake valves. This is because VTEC requires a third center rocker arm and cam lobe, and, in the SOHC engine, the spark plugs are situated between the two exhaust rocker arms, leaving no room for the VTEC rocker arm. Additionally, the center lobe on the camshaft cannot be utilized by both the intake and the exhaust, limiting the VTEC feature to one side. However, beginning with the J37A4 3.7L SOHC V6 engine introduced on all 2009 Acura TL WD models, SOHC VTEC was incorporated for use with intake and exhaust valves. The intake and exhaust rocker shafts contain primary and secondary intake and exhaust rocker arms, respectively. The primary rocker arm contains the VTEC switching piston, while the secondary rocker arm contains the return spring. The term primary does not refer to which rocker arm forces the valve down during low RPM engine operation. Rather, it refers to the rocker arm which contains the VTEC switching piston and receives oil from the rocker shaft. The primary exhaust rocker arm contacts a low-profile camshaft lobe during low RPM engine operation. Once VTEC engagement occurs, the oil pressure flowing from the exhaust rocker shaft into the primary exhaust rocker arm forces the VTEC switching piston into the secondary exhaust rocker arm, thereby locking both exhaust rocker arms together. The high-profile camshaft lobe which normally contacts the secondary exhaust rocker arm alone during low RPM engine operation is able to move both exhaust rocker arms together which are locked as a unit. The same occurs for the intake rocker shaft, except that the high-profile camshaft lobe operates the primary rocker arm. The difficulty of incorporating VTEC for both the intake and exhaust valves in a SOHC engine has been removed on the J37A4 by a novel design of the intake rocker arm. Each exhaust valve on the J37A4 corresponds to one primary and one secondary exhaust rocker arm. Therefore, there are a total of 12 primary exhaust rocker arms and 12 secondary exhaust rocker arms. However, each secondary intake rocker arm is shaped similar to a Y, which allows it to contact two intake valves at once. One primary intake rocker arm corresponds to each secondary intake rocker arm. As a result of this design, there are only 6 primary intake rocker arms and 6 secondary intake rocker arms. VTECE. The earliest VTEC implementation is a variation of SOHC VTEC which is used to increase combustion efficiency at lower PM while maintaining the mid-range performance of non-VTEC engines. VTEC is the first version of VTEC to employ the use of roller rocker arms, and because of that, it forgoes the need for having 3 intake lobes for actuating the 2 valves. 2 identical lobes for non-VTEC operation and 1 lobe for VTEC operation. Instead, there are 2 different intake cam profiles per cylinder. A very mild cam lobe with little lift and a normal cam lobe with moderate lift. Because of this, at lower PM, when VTEC is not engaged, one of the 2 intake valves is allowed to open only a very small amount due to the mild cam lobe, forcing most of the intake charge through the other open intake valve with the normal cam lobe. This induces swirl of the intake charge, which improves air-fuel atomization in the cylinder and allows for a leaner fuel mixture to be used. As the engine's speed and load increase, both valves are needed to supply a sufficient mixture. When engaging VTEC mode, a predefined threshold for mile per hour, RPM and load must be met before the computer actuates a solenoid which directs pressurized oil into a sliding pin, just like with the original VTEC. This sliding pin connects the intake rocker arm followers together so that now, both intake valves are now following the normal camshaft lobe instead of just one of them. When in VTEC, since the normal cam lobe has the same timing and lift as the intake cam lobes of the SOHC non-VTEC engines, both engines have identical performance in the upper power band assuming everything else is the same. With the later VTEC implementations, the only difference it has with the earlier VTEC is that the second normal cam profile has been replaced with a wild cam profile which is identical to the original VTEC wild cam profile. This in essence supersedes VTEC and the earlier VTEC implementation since the fuel and lower PM torque benefits of the earlier VTEC are combined with the high performance of the original VTEC. 3-stage VTEC. 3-stage VTEC is a version that employs 3 different cam profiles to control intake valve timing and lift. Due to this version of VTEC being designed around a SOHC valve head, space was limited and so VTEC can only modify the opening and closing of the intake valves. The low-end fuel economy improvements of VTEC and the performance of conventional VTEC are combined in this application. From idle to 2500-3000 RPM, depending on load conditions, one intake valve fully opens while the other opens just slightly, enough to prevent pooling of fuel behind the valve, also called 12-valve mode. This 12-valve mode results in swirl of the intake charge which increases combustion efficiency, resulting in improved low-end torque and better fuel economy. At 3000, 5400 RPM, depending on load, one of the VTEC solenoids engages, which causes the second valve to lock onto the first valve's camshaft lobe. Also called 4-valve mode, this method resembles a normal engine operating mode and improves the mid-range power curve. At 5500, 7000 RPM, the second VTEC solenoid engages so that both intake valves are using a middle, third camshaft lobe. The third lobe is tuned for high performance and provides peak power at the top end of the RPM range. IVTEC, Honda IVTEC has VTC continuously variable timing of camshaft phasing on the intake camshaft of Dohc VTEC engines. The technology first appeared on Honda's K-Series 4-cylinder engine family in 2001. In the United States, the technology debuted on the 2002 Honda CR-V. VTC controls of valve lift and valve duration are still limited to distinct low and high RPM profiles, but the intake camshaft is now capable of advancing between 25 and 50 degrees, depending upon engine configuration. Phasing is implemented by a computer-controlled, oil-driven adjustable cam sprocket. Both engine load and RPM affect VTEC. The intake phase varies from fully retarded at idle to somewhat advanced at full throttle and low RPM. The effect is further optimization of torque output, especially at low and mid-range RPM. There are 2 types of IVTEC K-Series engines which are explained in the next paragraph. K-Series. The K-Series engines have 2 different types of IVTEC systems implemented. The first is for the performance engines like in the RSX Type S or the Civic C, and the other is for economy engines found in the CR-V or Accord. The performance IVTEC system is basically the same as the Dohc VTEC system of the B16As. Both intake and exhaust have 3 cam lobes per cylinder. However, the valvetrain has the added benefit of roller rockers and continuously variable intake cam timing. Performance IVTEC is a combination of conventional Dohc VTEC with VTC. The economy IVTEC is more like the SOHC VTEC in that the intake cam has only 2 lobes, one very small and one larger, as well as no VTEC on the exhaust cam. The two types of engine are easily distinguishable by the factory-rated power output. The performance engines make around 200 HP or more in stock form, and the economy engines do not make much more than 160 HP from the factory. R-Series, IVTEC with variable cylinder management. In 2003, Honda introduced an IVTEC V6 that includes Honda's cylinder deactivation technology, which closes the valves on one bank of cylinders during light load and low speed operation. According to Honda, VCM technology works on the principle that a vehicle only requires a fraction of its power output at cruising speeds. The system electronically deactivates cylinders to reduce fuel consumption. The engine is able to run on 3, 4, or all 6 cylinders based on the power requirement, essentially getting the best of both worlds. V6 power when accelerating or climbing, as well as the efficiency of a smaller engine when cruising. The technology was originally introduced to the US on the 2005 Honda Odyssey minivan, and can now be found on the Honda Accord Hybrid, the 2006 Honda Pilot, and the 2008 Honda Accord. Example: EPA estimates for the 2011 V6 Accord are 24 mpg combined versus 27 in the two 4-cylinder equipped models. IVTEC VCM was also used in 1.3L 4-cylinder engines used in Honda Civic Hybrid. IVTEC-I, a version of IVTEC with direct injection, first used in 2003 Honda Stream. AVTEC, the AVTEC engine was first announced in 2006. It combines continuously variable valve lift and timing control with continuously variable phase control. Honda originally planned to produce vehicles with AVTEC engines within next 3 years. Although it was speculated that it would first be used in 2008 Honda Accord, the vehicle instead utilizes the existing IVTEC system. A related U.S. patent was filed on January 5, 2005. VTECO. The VTECO engine series included gasoline direct injection, turbocharger, variable valve motion technology such as VTEC. The engines were introduced in November 19, 2013 as part of the Earth Dreams technology range, which included 3 displacement capacities. Initial implementation for European vehicles included 2-liter 4-cylinder engine used in Honda Civic Type R, which included Euro 6 emissions compliance. VTEC in motorcycles. Apart from the Japanese market, only Honda CB400 SF Super 4 Hyper VTEC, introduced in 1999, the first worldwide implementation of VTEC technology in a motorcycle occurred with the introduction of Honda's VFR 800 sport bike in 2002. Similar to the SOHC VTEC style, one intake valve remains closed until a threshold of 7,000 RPMs is reached. Then the second valve is opened by an oil pressure-actuated pin. The dwell of the valves remains unchanged, as in the automobile VTECE, and little extra power is produced, but with a smoothing out of the torque curve. Critics maintain that VTEC adds little to the VFR experience, while increasing the engine's complexity. Honda seem to agree, as their VFR 1200, a model announced in October 2009, came to replace the VFR 800, which abandons the VTEC concept in favor of a large-capacity narrow V unicarm, that is, SOHC, engine. However, the 2015 VFR 800 will again sport the same VTEC system of the 2002 to 2009 VFR motorcycle. Honda incorporated the technology into the NC700 series, including the NC700D Integra, released in 2012, using a single camshaft to provide 2 timing routines for the intake valves. References. External links: Honda Tech pages, VTEC, IVTEC Dohc, S2002.0L Dohc VTEC, Type 2.0L Dohc IVTEC, 2.0L Dohc IVTECI. V6 3.0L IVTEC, V6 3.5L VTEC, Honda Technology Picture Book, VTEC, World Honda, New IVTEC Technology.